In example 6 from section 8.3, you're going to notice that they throw an even power of tangent at you with no other type of function present in the integrand. And to compound the matters a little bit, we've got boundaries of 0 and pi over 4 that we're going to have to consider as well. But since we've got an even power of tangent, fourth in this case, we're going to go ahead and proceed as we always have in trying to sort of break this apart and use squared powers of the tangent so that we can manipulate it further with some trigonometric integrals. So trigonometric identities. So what we're going to do at the very beginning is change the tangent of fourth to tangent squared of x times tangent squared of x. Now the motivation for doing that will become more apparent as we work through the problem. And the key, like I said before, is really having a really strong knowledge of your trigonometric identities, namely the fact that the tangent squared of x in this case is going to be equivalent to the secant squared of x minus 1. So we'll rewrite the second tangent of x using that identity. Now the next step, as with many of the steps that we've seen before, it seems maybe it's a little counterproductive, but it's going to be very important. We're going to go ahead and distribute this tangent squared. In essence, we're just multiplying the two parts of our integrand together. And in doing so, we would have, of course, tangent squared of x times secant squared of x minus the tangent squared of x, all with respect to x. Now, the reason why we did that, if you take a look at what you've got here in the first portion of the integrand, tangent squared times secant squared, that is a very doable integration. It's ready right now. If you let u be the tangent, the derivative of tangent is secant squared. You've got your perfect match. And in essence, you're just going to be integrating a u squared. So that's very simple. Now, for the other portion, tangent squared, that's not so simple. The integration of tangent squared isn't one of the typical trigonometric integration formulas that students know. It's just one step away, though, from being a pretty simple one. And so we're going to still have to mess around with our tangent squared. And to do that, we're going to do a step that we've already performed in the problem. We're going to rewrite tangent squared as secant squared minus 1. So let's go ahead and take care of that. So we've got a lot of sort of rewriting to do here. Tangent squared of x times secant squared of x will drop straight down. And then if we rewrite this, as I said, we've got to be careful because we have a negative sign, a minus, already in front. So if tangent squared is the same as secant squared minus 1, then I could go ahead and distribute this negative sign all throughout and take care of it as such. So you could think of this integrand as having three terms now, all three of which are relatively easy to integrate. Now for the first portion here, as I said before, the u is going to be the tangent of x, the derivative of it of which would simply be secant squared of x dx, and that's exactly what we were hoping for. We've got ourselves a very easy integral of u squared, essentially u squared in the integral. I'm just going to kind of sketch out what's happening here in terms of u because I'm going to take the integral pretty quickly and go ahead and back substitute my tangent of x in. So as you can see that this is going to be a u to the third over 3, I'm going to rewrite my brand new integrand over here, or my result of my integral over here now with the back substitution. So tangent of x will take the place of that u. So we have tangent cubed of x all over 3. Now as far as integrating the secant squared, not a lot of trouble with that. The integration of secant squared is simply tangent Remember, your motivation there is the fact that the derivative of tangent is secant squared, so the integral of secant squared would be tangent. And of course, the integration of 1 will give you x. And our boundaries, once again, go from pi over 4 to 0. Now we're pretty much home free. The only thing sort of in our way now is making sure that we know what the tangent of pi over 4 is. I'm sure that that's one of the easier ones which you deal with, but pi over 4 is nothing more than a 45-degree angle, correct? And you've got your two legs that then must be the same size. Ratios could be 1. The hypotenuse would be radical 2, but that doesn't come into play here since we're dealing with tangent. So long story short, the tangent of pi over 4 is nothing more than just 1 over 1, or 1. So when we plug pi over 4 in here and take the tangent and cube it, we still will find that we have 1 as our result. So we have 1/3 minus the tangent of pi over 4, which is 1, plus pi over 4. And then we'll subtract the result when we plug in 0. Unfortunately for us, not a lot to worry about there because the tangent of 0, of course, is 0, both here and here. And of course, the last term is going to sort of give us nothing else to worry about as well. So you're essentially subtracting 0 from that result. So when you go ahead and combine the like terms here, you'd get a negative 2/3 plus pi over 4. And nothing wrong with that answer. Looks good. A lot of times, though, they don't like that negative sign leading off for whatever reason, so they might flip things around and call it pi over 4 minus 2/3. I don't think getting a common denominator of 12 would be completely out of the question as a possible choice in a multiple choice type of assessment. Of course, the decimal approximation for this would work as well, 0.119. But again, if you had the capabilities to do that, you probably wouldn't have integrated this by hand anyway. So our answer is essentially going to be pi over 4 minus 2/3.